Okay, hello everyone. So this is the second session of the OpenSees tutorial, and in this session, so if you remember the first session, we learned how to do linear elastic analysis of 3D frame in OpenSees. We started by, setting up the OpenSees and Node++, and also I showed you how to integrate both, and then we got into how to develop a linear elastic 3D frame model in OpenSees and how to perform static and model analysis of this model. So in today's session, we're going to see how to perform nonlinear analysis of the reinforced concrete cross-section. More specifically, we'll do a moment curvature analysis of this section. And then the last session of this tutorial will be doing a nonlinear analysis of a 2D reinforced concrete beam. And after that, you'll be given a project to work on, an OpenSees project. If you remember, we changed the plan from 4 sessions into 3. In the original plan, we had the 4th session covering nonlinear analysis of a 3D frame. But thinking about it, that would be just integrating what we've done in the first session and in the second and third session. So basically, there's not going to be any new material covered if we do a session on nonlinear analysis of a 3D frame. So we adjust the plan a little bit to just have 3 sessions instead of 4. Okay, let's go into today's session. So RC section moment curvature analysis. If we have, a reinforced concrete cross section like this one applied or subjected to bending moment, then this is the strain distribution that we will get. Of course, this is assuming a linear, section plane remains plane after deformation assumption. And so if we make this assumption, then the strain distribution will always be linear across a cross section. This is something that Dr. Brahimian explained in the class. So this is, the strain distribution we would expect. We would have compression at the top and tension at the bottom. And basically the curvature in the class, Dr. Brahimian labels it by kappa, but here it's shown by phi instead. So basically, phi will be the section rotation. And then if we push the cross section to failure, this is the moment curvature curve that we would expect to get under monotonic loading. And so again, Dr. Brahimian discussed this in the class. At the beginning, we will have a linear curve, and this is basically when both the reinforced concrete and steel or reinforcing bars are still in the linear phase of their behavior. And then once we reach this point, and this is where the basically the concrete reaches its cracking strength. So basically that tensile strength of concrete. After that, the concrete starts cracking. And this is when we get into this phase of the response where the reinforcing bars are still in their linear phase, but the reinforced concrete is cracked. And then, we keep pushing until we reach this point, and this is when the reinforcing bars start yielding. And after this point, basically the whole cross section becomes nonlinear, both the concrete and the reinforcing bars. And then basically we can, we keep pushing until the failure of the cross section. So at this point, as I said, both the concrete and the steel are behaving linear elastically, and so this is the strain and stress distribution that we would expect. Both are linear. Now, after cracks happens, strain again still linear because of the plane section remains a plane after deformation assumption. So always the strain is linear, but then the stress is a little bit different now because we make this assumption that once the concrete starts cracking, then it has tensile strength, negligible tensile strength. So this is what's reflected here in the stress distribution. We are basically assuming that the tensile strength is zero in the concrete and that the concrete only carries compressive stress. And so, given this assumption, the tensile stress is only carried by the reinforcing bars. And then at this point where the steel starts yielding, of course, here the steel stress in the steel is less than the yielding strength of the steel because we're in this part. But once we reach this part, now the stress in the steel becomes equivalent to the yielding strength of the steel bars. And now, if we keep pushing, it just that the steel, of course, the if you are assuming perfect linear, perfectly plastic behavior for the steel bars, then the stress will still be equivalent to the yielding strength. If we're assuming, a bilinear curve, then of course the stress will be slightly larger than the yielding strength in the steel bars. Okay, this is basically what I just explained. First tensile crack in concrete and then crack section. And at this point, steel bars yield. And then here, we get spalling of the concrete cover. And after that, the cross section fails. Okay, in this session, this is the cross section that we're trying to model and simulate its behavior. In OpenSees, it's a square cross section with 16-inch width and depth. And we have reinforcing bars for number 9 bar at the bottom and the top. And the cover is 2.5 inch, and these are the properties of the steel. I field is 60 KSI, ES is 29,000 KSI, and the compressive strength is 5 KSI. And this is basically how we would model a cross section in OpenSees. Of course, this is not an element, so we don't need to use a regular element in OpenSees. It's just we're trying to simulate the behavior of a cross section. So for this purpose, we just define 2 points at the same with the same coordinates and connect them using a zero length element, and basically assign this predefined cross section to the zero length element. And we basically fix the 1 point and let the other points free to rotate. So basically we fix all degree of freedom at this node and then apply, except for the rotational degree of freedom. And then we apply a moment at this free rotational degree of freedom and record the response of this node to the applied moment. Okay, so how do we go about building this model and analyzing its response? Like before, we always start with the model builder command. In this command, we basically define the number of dimensions in the problem and also the number of degrees of freedom. So for this problem, we're just trying to simulate the cross section, so it can be done in 2D. Like if we go back here, this is just a 2D problem, right? Each node has, two axial or two translational degrees of freedom and one rotational degree of freedom. So we have a 2D problem. X and Y with 3 degrees of freedom for each node. So this is what we have here. We have two dimensions, X and Y, and 3 degrees of freedom for each node. Once we define the model builder, we can move on to defining the nodes. For this model, we just like I explained earlier, we have two nodes. One is fixed and the other one is free. So we have node number one at 0, 0, and then node number two at the same location. And the reason is that we're just looking at the behavior of the cross section. We don't have any element here, and so we just use a zero length element to define the cross section by assigning this cross section to the zero length element. Okay, then we move on to defining the material. This is a reinforced concrete cross section, so we have both concrete and reinforcing bars. So basically, we need a uniaxial material for steel and another one for concrete. So we have different steel and concrete material models in OpenSees. In this tutorial, we're just gonna work with steel O1 and steel O2 for steel reinforcing bars, and concrete O1 and concrete O2 for the concrete. This is, Dr. Brahimi has explained this in the class, but we're just gonna show them briefly here. Steel O1 material is just a bilinear simple bilinear material where we have the first part represents the linear elastic phase of the response, and the second part represents the nonlinear or the plastic part. Steel O2 is a little more advanced and complex than steel O1. Then we don't have a bilinear curve. Instead of having this sharp transition between the first part and the second part of the response, and steel O2 will have this nice smooth transition between the two phases. And of course, this is facilitated by introducing more hyperparameters in the material model. And then concrete O1, basically in this model, we just have compressive, part or strength, and it's assumed that the concrete doesn't carry any tensile stress, and that's why the tensile part of the material model is fixed to 0, so no tensile strength here. Concrete O2 is a little bit more, complex. It's basically, in addition to simulating the compressive strength of concrete, it also gives us the ability to simulate the tensile strength by introducing these additional parameters. FT, the tensile strength, and ETS is basically the stiffness in this unloading part of the tensile, part of the response of the concrete material. Okay, this is how we define these different materials. It's steel O1, we just need the yield, yield strength, the modulus of elasticity, and B is the ratio between this stiffness and this stiffness. These are additional parameters that we can use, but they're optional. Steel O2, we add some, additional parameters to be able to add this smooth transition feature. And this is basically done through these additional parameters, R0, R1, and R2. And the values or recommended values of these parameters, we can check the OpenSees website for that, the steel O2. Here it's recommended that R0 is 10 or between 10 and 20. Usually we use a number around 18. But of course, it depends on the problem. So you can play with this number to like if you have a problem with maybe experimental results, Then you need to play with these parameters to get the results as close as possible to the experimental data, which we have in this case. The not really. There's gonna be something that we will cover in the next session when we simulate the response of cantilever beam. For this cantilever beam, you have experimental data for Popov beam. Popov is a researcher, and he did experimental study on a cantilever beam. So for this session, we will have the experimental data. So you'll see that you will need to adjust the values for these different parameters to get as close match to the experimental data as possible. So basically, you can use a value between 10 and 20 for R0. For now, you can use, maybe 18 or something. And then R1 is 0.925 and R2 is 0.15. Okay. So this is for steel O2, and then concrete O1, we just need the compressive strength and the strain corresponding to this strength. And then this is the crushing strength and the strain corresponding to this strength, basically this point. So this is the strength of this point and the corresponding strain. Concreto 2, a bit more complex. Now we have additional parameters to simulate this part. So the first 1, 2, 3, 4 parameters just similar to Concreto 01. But then we have these additional parameters, lambda, FT, and ETS. And so FT and ETS are, the strengths at this point and this, slope or, stiffness. And then lambda basically helps you to also simulate this part of the response, which is a factor, as a function of the initial stiffness of the concrete. Okay, so this is how we define the different types of material. And of course, for simulating the response of this cross-section, you're welcome to try different combinations of these 4 materials and compare the response of the cross-section and see how they differ. And also, you need to think about why you're observing these differences and what does that have to do with these different types of materials. Okay, so once we define the materials or material models, we can move on to defining the cross-section. This is the cross-section we're trying to simulate here. And to model this cross-section, we use the fiber section on OpenSees. And the reason we're using fiber section, and this is again something that Ibrahim explained in the class, is that fiber section allows you to consider the interaction between the bending and axial loads. So in this case, we're developing this fiber section to model the cross section. And as you can see, the concrete is modeled using these different fibers, and the steel bars are using these fibers. And the reason we're dividing this cross section in this direction and not in this direction is basically because the applied moment the moment is applied in this direction, so it causes a stress variation along this dimension. And that's why, to capture or to accurately capture this variation, we divide or subdivide the cross section in that direction. However, because we don't have any moment applied in this direction, then there's no stress variation across the widths of the cross section, and that's why we don't need to subdivide the cross section in this direction, because there's no variation to capture here. However, if we have 2 moments applied in both directions, in this case, we would need to also subdivide the cross section in that direction as well. Okay, so how could we define cross section in OpenSees? This is the command to use section fiber. You give it some tag, you just a unique number for this specific cross section. And then within this section, we can basically model both concrete and steel bars. We have these different comments for that. Fiber is used for defining the reinforcing bars. And then also layer is another way of defining the reinforcing bars. And I'm going to explain the difference between both and the advantages and disadvantages of using either of them. And then the patch is the command to use for defining the reinforced concrete. Let's see how these commands are defined. So the fiber, the way to define it is to basically um, specify the Y and Z locations for the reinforcing bar. This because here we have we're assuming that this is the Y axis and this is Z axis. So basically for each bar you specify the Y and Z coordinates, and then the A is the cross-sectional area of the bar, and mat tag is the tag of the material that we defined earlier. So before we define the cross-section, we need to define the material models first, and then use them in defining both the steel bars and concrete. So in this case, that would be the tag of steel O1 or steel O2 materials that we already defined. So as you can see, a potential problem of this way of modeling the reinforcing bars is that now to model 8 reinforcing bars, you have to use 8 different commands or 8 different fiber commands. Each one models a single reinforcing bar. And basically, a more efficient way of doing this is using the layer command. And in this case, basically, in cases where you have a uniform distribution of bars, like what we have here, uniform distribution meaning that the distance between each two bars is the same. We have these are 3 identical distances. So we have uniform distribution. So in this case, you can just use this layer command to model this whole layer of 4 bars in just one command. So you do this by saying layer straight, give it unique tag, and then the number of fiber, meaning the number of reinforcing bars in this specific layer. So here we have 4 bars in the layer. And then, so the number of bars, and then the cross-sectional area of each bar. So also another assumption is that the cross-sectional area is the same for all bars. So if you have a case where we have different bars with different cross-sectional areas, then we cannot use this layer command. So this is another assumption that the cross-sectional area is the same. So this is what we specify here. And then you basically specify the first and end point, or the start and end points of this layer. So for this layer, that will be the start point and the end point. So you give it the Y and Z coordinates of the start point and the Y and Z coordinates of the end point. So in this case, we have 8 bars. We can just use 2 layer comments to model these 8 bars compared to 8 fiber comments to model the same bars. So you can see how efficient this command is for modeling steel bars. Of course, given that the assumptions that we just discussed are enforced. Like we have uniform distribution and same cross-sectional area. Okay, so this is now how we define the steel bars. Now let's move on to defining the reinforced concrete. This is the command we use for that, patch rectangular. So actually we have 2 different versions of this command. So let's just discuss this one first, and then We'll explain the other one after that. So patch is this patch rectangular is assuming that the um, cross-sectional concrete is the cross-sectional geometry of the concrete material is rectangular. This is why we have this rect, and then you give it the unique tag, and then the number of subdivision in both y and z directions. So in this case, we have in the y direction we have 1, 2, 3, 4, 5, 6, 7. Uh, sorry, 4, 5, 6, 7, 8, 9. So we have 9 here in this y direction, and then in z direction just one. And then you give it the coordinates of the two opposite corners of this cross section. So for this case, point I would be, let's say this point, and point J would be this one. Of course, you cannot use this one and this one, for example, because this way, you know, um, basically you're not giving it any information about the depth of the cross section, just the width. So that's why we need to define two opposite corners of the rectangular cross section. Now let's assume that you have another non-rectangular cross section. The way to deal with this non-like uniform cross sections is let's go to fiber patch. So this is the one that I just explained, and this works only for rectangular cross section. You just specify these 2 points. Now, if you have a more, like we need a more general way of modeling concrete cross sections, is this patch quad. And this doesn't assume a rectangular shape, so it can model any kind of shape. And one condition here is that the way to model this non-uniform, you have to define the four corners of the cross section, and the way to or the order in which you need to define them is in a counterclockwise sequence, meaning that if you start, let's say you start at this point I, then you go from I counterclockwise I, J, K, L. Okay, this is very important that you define these four nodes in the correct sequence to make sure that you don't mess up the analysis results. And also another very important note here is that this is given that the y and z directions are specified in this way. So if you rotate, then this is gonna affect the order in which you define these nodes. Okay. But of course, for our problem, we have a rectangular cross section, so you can just use the patch rectangular command. Okay, so this is basically how this looks like. You start by defining variables for the cross section. This is the width, the depth, and then the cover, and then the cross-sectional area of the number 9 bars, which is 1 inch squared. And then Y1 is basically half the depth of the cross section, Z1 half the width. And then we can define the section fiber. This is the tag. It has to be unique. So if you have different sections, you need to give each one a different tag. And then, we can define the concrete using the patch rect. Give it a tag. I'm sorry, this is a material tag of the concrete. Not a tag for the patch. This is material tag that you defined already, and then number of subdivision in the y and z directions, and then the coordinates of the first and end nodes. Now, for the enforcing bars, in this case, we're using the layer straight material tag, the steel material, and then number of fibers 4, and then the cross-section area of the fiber that we already defined, and then the coordinates of the first and last nodes. So this would be the y and z coordinate of the first node and y and z coordinate of the last node. And we do the same so this is for the top layer, and then we do the same for the bottom layer. The only difference would be the nodes that we for the coordinates for the first and end nodes. Everything else will be the same. Okay, so this is how we define cross section. Now, once we define the cross section, we define the zero length elements that we talked about earlier, connecting these two nodes. So we have two different kinds of zero length elements in OpenSees. If you have an element and the way you want to specify or characterize the behavior of this element is through some, linear elastic maybe material, like in case you're defining a spring or a dashboard, and you wanna just assign some linear elastic material for the behavior of the spring or the dashboard, then the way to do this is through zero length elements, not zero length section. So if you go to OpenSees here, you will see that there is go to element. You have the zero length element. For this element, you can just characterize its behavior using some I'm sorry, material tag, and that's it. And this is good for applications like where you have to define springs or dashboards. But in this case, we want the to characterize the behavior of this element using cross section. And for this, we have different type of zero length element, which is the zero length section. And so in this element, you can characterize its behavior using a predefined or a tag of a predefined cross section. So basically, whatever we defined, the cross section that we defined here, we use the tag of this cross section when we define this zero element section element. So we have zero length section. You give it a unique tag, and then this is the first and end nodes of this element. In this case, that will be 1 and 2. And then you give it the tag of the predefined cross section. And these are additional parameters that you might define if needed for your application, but we don't need it for our application. Okay, so this is how you define the element, a tag for the element, the first and end nodes, and then the tag of the cross section we defined earlier. Okay, so this is how the element is defined, and then we can move on to defining the load applied to the cross section. In this case, we have a moment, and we want to apply a both monotonic and cyclic loading. So let's see how can we define this. So since this is basically a static problem, we want to apply this monotonic and cyclic moments statically. So for this, we can start by defining a plain load pattern. And then within this load pattern, we have different commands. So in this case, we just want to use this load, which is used to define nodal loads, which is the case here. So basically, this is what we use, and we give it the node tag. We want to apply this load to node number 2, so that would be the tag here. And then we specify which degree of freedom this moment is applied to and the load factor associated with this applied load. So one thing to note here is that when you apply, we will see later that the way we apply this is through displacement control. And displacement control is basically you specify the displacement or deformation that you want the cross section to undergo, and then record the corresponding stress or corresponding loads to this applied displacement or deformation. So basically, we apply displacement, and we can only record the deformation of this of this free node. So now the question is, how can we apply the corresponding moment at this node using just the recorder that records the deformation. Of course, this is a free node, so there's no reactions here. But we want to think about a way to also record the also record the corresponding moment to the rotation of the node. So the way to do this is that like if you remember from the last session, we when we were explaining the recorders, we said that I mean maybe you can go to OpenSees and output recorder. So this is how we define a node recorder. And one of the optional features that we can use here is time, and this basically records the deformation and the corresponding time to this deformation. So we're gonna do a trick here in which we're gonna try to see how to record the load using this time feature in the node recorder. And the way to do this is basically to try to define a relationship between the load and the time. So if we have a linear relationship, uh, basically, the load is varying linearly with time. That means that the recorded time will correspond to the load on this node. And so how we define this relationship is basically through the load pattern. This is how we define the load pattern, linear, meaning that we have this linear relationship between time and load. And we, give it a factor of 1. And then here, the way we define it is that we have this load applied at the node number 2 in the rotational direction, which is the third degree of freedom here. And we want to make sure that the factor here is 1, so that we have this nice, 45 degree line between the time and the load. If we do this and we record the rotation or deformation of node number 2, using this, time feature, basically we will be recording the time versus deformation, and the recorded time will correspond to the applied moment on this node. Okay. Another and maybe simpler way to do it is to just record the reaction at the fixed node, and basically the moment recorded at the this node will be the moment applied on the cross section. So you can use either ways, and maybe it's a good exercise to do both and see if they give you the same results for the moment. Okay. Once we're done defining the elements and the load pattern, we can move on to defining the constraints. So in this case, we have just need to fix all degrees of freedom at node number 1. And node number 2, we're fixing the translation in the X and Y directions, and we're keeping the rotational degree freedom free. Then we can define the constraints. In this problem, we can just use the plain constraints. Of course, there are more advanced constraint, handlers in OpenSees like transformation and Lagrange, using Lagrange multipliers and other methods. And these are methods suitable for more complex, applications. But in our application here, plain is, sufficient for enforcing these kind of constraints, which in this case we have just fixed degrees of freedom at certain nodes. Okay, and then number, we have plain RCM. In this case, we can use RCM. We talked about this in the previous session, is that RCM is better for basically it numbers the degrees of freedom in the system in a way that makes the resulting stiffness matrix a banded one. And of course, this bandedness feature of the stiffness matrix is can be manipulated later in when solving the system of equations in a way that only consider the banded part of the matrix and neglects the zero parts. And this way we can save a lot of computational time. Of course, this is a very simple problem, so it's not really going to make much difference using plain or RCM. But just let's stick with RCM. And then system band general. Band general is related to this. Is that this is a way of or an algorithm for solving the system of equations in a way that only exploits this bandedness feature of the stiffness matrix to only work on the banded part and neglects the zero part. And then integrator we have for static problems, we have load and displacement control. So this is the kind of behavior that we would expect for our problem. We have a nonlinear problem, so after a certain point, the response doesn't, or the strength doesn't go up. In fact, it stays constant or it even goes down. So if we use a load control for this kind of problems, we will face issues once we cross this point in the response curve because we cannot increase the loads beyond this point. And that's why for these type of problems, it's better to use displacement control because there's no limit on how we can increase the displacement or the deformation of the cross section. So for our problem, we're gonna just use displacement control. And so the way this is how to define displacement control integrator of OpenSees. You specify the node at which you want to apply the node and degree of freedom of this node that at which you want to apply the displacement, and then the increment at which you're applying the displacement. And so in our problem, we have node number 2 and the rotational degree of freedom, which is 3, and then some increment of displacement. And the way we to define this increment has to do with the yielding point or the yielding deformation of the cross section. So we need to find this value and then determine the value for the increment as a function of this yielding, maybe, I don't know, like yielding over 20 or 50, or it's a fraction of the yielding deformation or rotation of the cross section. And then once we define the integrator, we need to define the algorithm. You have different algorithms in OpenSees, and this is something Dr. Ibrahimian covered in the class. Newton, modified Newton. You can use either. Then we define the convergence test. Of course, our preferred one is the relative norm displacement increment, or maybe relative norm energy, if you want. And then we define the recorder. Basically, the recorder here, we're trying to record the response of node 2 at degree of freedom number 3. So this is what we do here, the time and displacement and degree of freedom 3 of node number 2. And then once we're done with this, we can basically define the analysis comments. Analysis, in this case, we have type static, because we're doing static analysis or quasi-static analysis. And then we analyze using the number of increments, which again is based on the yielding rotation. So as you can see, we need to find this value. One way of doing it is using these code-based equations. And as you can see, the yielding curvature here is a function of the yielding strain of the cross-section. In this case, 0.0021 for an enforced concrete cross-section. Divided by 0.6 multiplied by the depth of the cross-section. And in this case, 13.5 is basically the depth of the cross-section 16 minus the cover. And so this basically gives us some empirical or code-based estimate of the yielding curvature. And using the same code-based equations, we can also estimate the yielding moment and ultimate moment, but we don't really need these values. All what we need is the yielding curvature. Okay, once we have all this information, we can do both monotonic and cyclic analysis. Monotonic is quite straightforward. You just, push the cross section to a point that's a multiple of the yielding, curvature. So it could be, twice, three times, or four times the yielding curvature. This is the point to which you push your the cross section. Cyclic loading is a bit tricky because you're basically pushing the cross section in different directions. So this is the way we do it. Basically, here we're assuming you have three, wanna simulate the response of the cross section for the three cycles. So in the first one, we go twice the yielding cross section, and then we go in the negative direction four times, and then positive direction six times, and then negative eight times, 10 times, and then negative 12 times. And so that would be the curve that we expect to have. So here, this is at, twice, and then negative four bring us to this point. Six times in the positive direction, uh, bring us to this point, and then negative eight, and then 10, and then finally negative 12. Now, of course, you might think that why are we getting these, this little spike here, or this change in the stiffness of the cross section? So these are the kind of question you need to ask yourself, and they most likely have to do with the type of material model that you're using. So using different material models will give you this kind of like, a slightly different behavior, and so you need to look at these issues and think about them, and see how they relate to the type of material model you're using. Okay, so this is basically on this is the theoretical part of this session. I'm gonna show you quickly a model I developed for this and analyze it together. So I have two models, one for doing monotonic analysis and the other one for cyclic. I'm sorry if this name is misleading. Well, by this I meant monotonic. So basically, we start by using the wipe command, and this makes sure that it erases any information recorded from previous analysis, and make sure you start fresh. So this is a good practice whenever you develop a new model in OpenSees and run new analysis. You want to use this wipe command at the beginning, and then we, like I explained, we use the model builder with 2 dimensions and 3 degrees of freedom, and then we define the nodes, node 1 and 2, and then we move on to defining the different material models here, steel O1 and steel O2. As you can see, this part is the same, is shared between the two material models, but in steel O2, we use additional parameters to characterize this, smooth transition. These are the R0, R1, and R2 parameters. And then we have the concrete material models, O1 and O2. Just like here, the two models share the same parts, and then the O2 have additional parameters to characterize the tensile parts of the response. Here it's very important to notice that the compressive parameters are negative. So just make sure that you're very careful about how about the sign of the stress and strain. For compression, we use negative. For tension, we use positive. If you mix this up, it will mess up the the whole model and the analysis results. So just be careful about the signs here. Once we define the material, now we define the cross section. Just this is what I explained. We have the width, depth, cover, cross-sectional area of reinforcing bar. This is have the width and depth of the cross-section, and then we use these variables to define the section. Here we're defining a section fiber. We give it a tag of 1, and then this patch is used to define the concrete part of the cross-section. Um, this is the basically the tag of the concrete material, 3, and number of subdivisions in y and z directions, and then the coordinates of the first and the end node, the two opposing corners of the cross section. And then we define the steel bars or the reinforcing bars. Here we have layer for the or layer comment for the top layer and another comment for the bottom layer. This is the tag of the steel material, in this case steel O1. So basically in the model in its current form is using steel O1 and steel O2 material. Of course, you can play with this and change this to 4 or this to 2 to use steel O2 and concrete O2. And also you can play and try different combinations of these 4 material models and see how they affect the response. Okay, and then here we have the number of enforcing bars, which is 4, cross-section area of the bar, and then the coordinates of the 4 nodes. As you can see here, yeah, I'm sorry, this is the coordinates of the first and end nodes of the layer. Once we define the section, we can define the zero length section element. And this is basically the tag of the element, the first and end node, and this is the cross-sectional tag, which is this tag of the section that we defined earlier. And then we can move on to defining the pattern, load pattern. Here we're using plain pattern. This is a unique tag for the pattern, linear, and factor of 1. And the load is applied at node number 2 in the third or rotational degree of freedom. And using a factor of 1 here ensures, a 45-degree line between the time and load, as I explained earlier, which means that the recorded time, when we define the recorder here, the recorded time will correspond to the moment applied on node number 2 at the third degree of freedom. So this is a node recorder. I call it static here, corresponding to this model. And node number 2 in degree of freedom 3, and we want to record the displacement in this degree of freedom, which is the rotation, sectional rotation, or curvature. Okay, and then we define the constraints. We're constraining the node number 1 in all degrees of freedom, and node number 2 in the translation degrees of freedom, and we're keeping the rotation degree of freedom free to rotate. Constraint is plain, number RCM, set and band general. And then we want to specify the increments, which, like we explained, it has to be a fraction of the yielding curvature. In this case, I just using the values we got from here, 4.3, 10 to minus 4. So this is the yielding curvature, and I'm assuming that I want to do the analysis in 100 number of increments. And so basically, this is the increment that we're using when defining the integrator. And so the increment here is basically 5 times this yielding curvature divided by the number of increments. So basically, I'm trying to push the cross section here 5 times the yielding point or the yielding curvature. And I want to achieve this in 100 number of increments. This is what this means. So the total analysis will be done in 100, and the final point needs to be 5 times the yielding curvature. And basically, I'm using this to define the size of the increment as defined as the total curvature by the number of increment, which is 100 in this case. So we use this value when defining the displacement control. And then in this case, I'm using a Newton algorithm. Test is a relative displacement, normal displacement increment with this tolerance and this number of iterations. And then analysis is static, and then analyze nodes using this total number of increment, which is 100. And this is basically, this command gives us a flag that indicates if the model converges or not. So when you do analyze, there's an option to return a flag that indicates if the model converged. If it converged, it gives you zero. Um, I mean, we can look at it here. No analyze, I think. Um, yeah, so basically this is JD. Sorry, JD, one of the optional commands. So if it returns zero, this means that the analysis was successful and the model converged. If it's less than zero, it means that it's not successful. So basically here, what I'm doing is that I'm assigning the results of this to this new variable and printing this variable to see if the model converged. Okay, so let's run the model and see what we get. Um, yeah, so you see we got zero here, which is the result of this printing command in Tickle. Since we got zero, it means that the model converged and the analysis was successful. Okay, and we can just go to the folder where this is stored. Is it here? No. Yeah, this is what we have here. So let's have a look at the this response. So like I said, this is the first column which records the time. So in this case, this time is basically the applied moment on the cross section, and with the corresponding deformation. So if we plot this, we probably need the moment to be on the y-axis, so we should bring it here. And then if we plot this is what we get. And so, like you see, because we're using steel O1 and steel O2, this is bilinear curve. Of course, this is not going to be the case if we're using steel O2. This will look, it will have some transition. I mean, we can look at it here. Let's use 2 in the layer, which is steel O2, right? So if we use 2 here, now let's run the model again and see what we get. Um, so this is the moment, and this is the deformation. So you see this transition. Probably it's not that obvious here, but maybe we can change the parameters. And this is something I explained earlier, right? So if we look at steel O2, you'll see which parameter corresponds to having or how each parameter affects this smoothness of the transition from different parts of the response. Um, Steel O2, R20, R5. So you see R5, uh, now it makes the transition more obvious. So let's try R5 here. And let's look at the response again. Yeah, so now you see it went from here to there. And so Of course, the choice of the values of these parameters shouldn't be arbitrary. It should always be calibrated using experimental data, which is something that we're going to cover in the next session. When we simulate the response of a cantilever beam, it will be your assignment to basically play with these parameters and see the optimal values that gives you, response that's close to the experimental data. Okay, so this is for the static part. Or the monotonic part. Let's move into the cyclic response. The model is just defined as previous as the monotonic for the model is the same. It's just the only difference is how we apply the load. Now we have monotonic load, right? And the way we apply the monotonic load is like this. Okay, so we have a list of the basically the magnitude of the displacement that we want the cross section to reach in each cycle. So here I want to apply 2 and then -4. Of course, this is as a function of the yielding curvature. So we want to apply twice the yielding curvature and then -4 and then 6, -8, 10, and -12. And here the increment will be slightly different to reflect this difference in the applied load. So we start by, this is just the original increment that, as we defined earlier, we have this. Okay, let's look at this. The yielding curvature here is defined as the just this is the equation I showed you earlier here. Epsilon yield over 0.6 d. This is what we have here. Epsilon yield over 0.6 the depth, and then this is the number of increment, and then we define the increment size using the yield curvature divided by the number of increments. Now, if you remember that here, the way we define the size is basically applying this scaling factor multiplied by the yielding curvature divided by the number of increments. So this is exactly what we're doing here, right? So here we're defining this original curvature as yield of a number of increments. And then in this cycle, we just apply or multiply this by the scaling factor, which is defined in this list. So in this case, because it's monotonic, we have just a scaling factor of 5. Scaling factor here differs based on the step we're at in this cyclic list. So in the first step, it would be 2. So you're basically multiplying the scaling factor by the original increment size, and this is how you define the new increment size that you use when you defining in the integrator, the displacement control integrator. So in the first loop or the first step, we will have this as 2 and then -4 and then 6, and that's why you push the cross section in different directions at each step. And of course, this also will include the sign. So sometimes this will be positive, meaning that the cross section is being pushed in the positive direction. When it's negative, then it's basically being pushed in the opposite or negative direction, and so on and so forth. And then I'll analyze the cross section for this number of increment 100. And then again, this gives us an indication of whether the model converged or not. So basically, this analysis will be repeated 1, 2, 3, 4, 5, 6 times to complete the cyclic analysis. So if we run this model, so you see we have 6 different zeros here, meaning that the model converged in all these steps of the cyclic analysis. So if we go to the response of the folder, this is the response we have for cyclic. Can delete this. Again, move the moment to here to have it on the y-axis. And then let's plot this. So this is what you get. This is basically 2, -4, 6, -8, 10, and then -12. Of course, if you compare this to what we have here in the presentation file, you see these two are not exactly the same, right? So this is like nice bilinear hysteresis loop, which is different from here. As I said before, this has to do with the material model that you're using. So this is something that you need to explore on your own. Please try different combinations of concrete and steel material models, see how they affect the response, and try to think about, how and why is the response different when using different combinations of material models. And this is basically a part of your assignment for this session, is to repeat what we did in the session of monotonic and cyclic loading for this cross section. Try different steel and concrete materials, try different nonlinear analysis algorithms, try different conversion tests and tolerances, and try to see and understand how or what kind of effect they have on the results of the analysis. Okay, and this concludes session 2 of this tutorial, and I'm gonna share the models with you, and so you can basically use them to do this assignment and try these different algorithms and models, and try to understand how they affect the results. The next session will be basically doing nonlinear analysis of a cantilever beam, and will be the last session in this tutorial. And after after this, Dr. Brahmian will give you an OpenSees project to do and finish by the end of the semester. If you have any question, please don't hesitate to contact me, and I will be happy to help. Thank you, and have a good day.